Download this code from codegive.com, link in the description below. OK, let's dive deep into hashing, hash collisions, and compare md5 and sha256 with code examples. This will be a comprehensive guide. Part 1, Understanding hashing. What is hashing? Hashing is a fundamental concept in computer science and cryptography. It's a one-way function that takes an input, data of any size, like a file, a password, a string, and produces a fixed size output called a hash value, also known as a hash code, digest, or checksum. Think of it like a fingerprint for your data. Ideally, deterministic the same input always produces the same hash output. Efficient hashing algorithms are designed to be fast to compute. Preimage resistance, one way it should be computationally infeasible to find the original input data given only the hash value. You can't reverse the hash. Second preimage resistance given an input x and its hash h, x, it should be computationally infeasible to find a different input y such that h, y, equals h, x. Collision resistance it should be computationally infeasible to find two different inputs x and y such that h, x, equals h, y. This is the strongest requirement. Why use hashing? Hashing has many applications. Data integrity you can hash a file or piece of data and store the hash value separately. Later, you can rehash the data and compare it to the stored hash. If the hashes match, you know the data hasn't been modified. This is how file integrity checks and software distribution checksums work. Password storage passwords are never stored in plain text. Instead, they are hashed. When a user enters a password, it's hashed, and the resulting hash is compared to the stored hash. This protects the actual password from being revealed if the database is compromised. Note, modern password storage also uses salting and key derivation functions, which we'll touch on later. Data structures, hash tables hashing is the core of hash table implementations. It allows for fast lookup of data elements by transforming a key into an index into an array. Cryptography hashing is used as a building block in many cryptographic algorithms, such as message authentication codes, MACs, digital signatures, and key derivation functions, KDFs. Data deduplication cloud storage providers and other systems can use hashing to identify and remove duplicate data blocks, saving storage space. Content addressing, IPFS hashing is used to create unique content identifiers, allowing data to be retrieved based on its content rather than its location. Part 2, Hash collisions. What is a hash collision? A hash collision occurs when two different inputs produce the same hash output. Since the hash function maps an input of arbitrary length to a fixed size output, collisions are inevitable. The question is, how likely are they? Think of it like this: imagine you have a room full of people, and you assign each person a birthday, day of the year. Even though there are 365 possible birthdays, if you have enough people in the room, there's a good chance that two people will share the same birthday. This is the birthday paradox. The birthday paradox. The birthday paradox states that in a set of n randomly chosen people, the probability that at least two people will share a birthday is surprisingly high, even for relatively small values of n. The formula for the probability of no collision is, and the probability of at least one collision is. You can generalize this to hashing. If you have a hash function that produces n possible outputs, then the probability of a collision increases rapidly as you hash more and more inputs. Why are collisions important? Asterisk security implications. Asterisk if an attacker can deliberately create collisions, they can potentially compromise the integrity of systems that rely on hashing. For example, asterisk password attacks. Asterisk in older systems using weak hashing algorithms, like md5 without salting, an attacker could pre-compute a table of common passwords and their hashes, a rainbow table. When they obtain the password hashes from a database, they can look up the corresponding plaintext password in their rainbow table if a collision occurs. Asterisk digital signature forgery. Asterisk if an attacker can create a collision such that a benign document and a malicious document have the same hash, they could potentially trick someone into signing the malicious document. Asterisk denial of service. Asterisk an attacker can flood a hash table with inputs that all hash to the same location, causing extreme slowdown in lookup operations. Asterisk data integrity. Asterisk collisions can lead to data corruption if a system relies on unique hashes to identify and store data. Part 3, MD5 and SHA256. MD5, Message Digest Algorithm 5. Asterisk history. Asterisk developed in 1991 by Ronald Rivest. Asterisk output size. Asterisk 128 bits, 16 bytes. Asterisk status. Asterisk broken. MD5 is considered cryptographically broken. It is relatively easy to find collisions. Don't use it for security critical applications. It's still sometimes used for basic checksums, file integrity, where security is not a primary concern. Asterisk vulnerability. Asterisk researchers have developed techniques to create collisions in MD5 very quickly. Tools are available that can generate two different files that produce the same MD5 hash. SHA256, Secure Hash Algorithm 256-bit. Asterisk history. Asterisk developed by the National Security Agency, NSA, and published in 2001. Part of the SHA2 family. Asterisk output size. Asterisk 256 bits, 32 bytes. Asterisk status. Asterisk still considered secure. While SHA256 has not been completely proven to be collision resistant, no practical attacks have been demonstrated that can find collisions in SHA256 in a reasonable amount of time. It's widely used in cryptography and security applications. Asterisk family. Asterisk SHA256 is part of a family of hash functions that includes SHA224, SHA384, and SHA512, which produce outputs of different sizes. SHA3 is a different family of hash functions that was designed as an alternative to SHA2. Why is SHA256 more secure? One larger output size. Asterisk SHA256 has a 256-bit output compared to MD5's 128-bit output. This means that SHA256 has a much larger hash space, 2 sub 256/sub possible hash values, than MD5, 2 sub 128/sub possible hash values. The larger the hash space, the more difficult it is to find collisions. Two more complex algorithm. Asterisk SHA256 internal structure is more complex and resistant to the types of cryptanalytic attacks that have been successfully used against MD5. 3 no known practical attacks. Asterisk while theoretical attacks against SHA256 have been proposed, none of them are practical enough to be used to generate collisions in a reasonable amount of time. Part 4, Collision probability and practical implications. Probability of collision. Let's use the birthday paradox to estimate the number of hashes required to have a significant chance of finding a collision. Asterisk MD5, 128-bit. The hash space is 2 sub 128/sub. According to the birthday paradox, you need to hash approximately 2 sub 64/sub inputs, half the number of bits in the hash, to have about a 50% chance of finding a collision. 2 sub 64/sub is a very large number, but modern computing power can achieve this in a manageable time frame. Asterisk sha256, 256-bit. The hash space is 2 sub 256 / sub. You would need to hash approximately 2 sub 128 / sub inputs to have a 50% chance of finding a collision. 2 sub 128 / sub is an astronomically large number, far beyond current computational capabilities. This is why sha256 is considered much more secure. Practical implications. md5 You should never use md5 for security critical applications like password storage, digital signatures, or message authentication. There are far better alternatives. sha256 sha256 is still considered a strong hash function and is widely used in various security applications. However, keep in mind that no hash function is immune to collisions forever. As computing power increases and new cryptanalytic techniques are developed, the security of sha256 may eventually be compromised. That's why research into new and stronger hash functions, like SHA-3, is ongoing. Salting passwords. To further protect passwords, you should always use a salt when hashing passwords. A salt is a random string that is added to the password before hashing. This makes it much more difficult for attackers to use pre-computed rainbow tables or other collision attacks to crack passwords, even if the hash function itself is somewhat weak. Modern password storage should use key derivation functions, KDFs, like bcrypt, scrypt, argon2, which are specifically designed to be slow and computationally expensive, making password cracking even harder. Part 5, Code Examples, Python. Here's how to use md5 and sha256 in Python. Explanation of the code. 1. Import hashlib. Imports the hashlib module, which provides various hashing algorithms in Python. 2. _string md5, input string, asterisk. Asterisk takes an input string. Asterisk input string dot encode, UTF-8, encodes the string into bytes using UTF-8 encoding. Hashing algorithms operate on bytes, not strings. Asterisk hashlib.md5, encoded string, creates an md5 hash object. Asterisk .hexdigest, returns the hash value as a hexadecimal string. 3. _string sha256, input string, asterisk similar to _string md5, but uses sha256. 4. Main, asterisk. Asterisk demonstrates hashing a simple message using both md5 and sha256. Asterisk shows how to use the functions. Asterisk demonstrates salting a password for better security. Asterisk tries to demonstrate collisions, but very unlikely in simple example. Important notes about the code. Asterisk encoding. Always encode your strings to bytes before hashing. Different encodings, UTF-8, ASCII, etc., will produce different hash values. Salting. The salting example is a simplified illustration. In real-world applications, you should generate a unique and random salt for each user. Store the salt along with the hashed password, usually in the same database table. You'll need the salt to verify the password when the user logs in. Use key derivation functions like bcrypt, scrypt, or argon2, which handle salting automatically. Collision demonstration. The collision demonstration is unlikely to produce a real collision with the small change in input. Creating intentional MD5 collisions is possible with specialized tools, but it's not something you'd typically do in regular code. Part 6, Beyond SHA-256, Modern Hashing Practices. *SHA-3 *SHA-3, Cupcake is a different family of hash functions that was selected by NIST, National Institute of Standards and Technology, as the winner of a competition to find an alternative to SHA-2. It has a different internal structure and may be more resistant to future attacks. *Blake3 is a modern, fast, and secure hash function that is designed to be a drop-in replacement for md5, SHA-1, SHA-2, and SHA-3. It's worth investigating. Key derivation functions, KDFs. When hashing passwords, never use plain hash functions like md5 or sha256 directly. Use a KDF like bcrypt, scrypt, or argon2. These KDFs are specifically designed to be slow and computationally expensive, making password cracking more difficult. They also handle salting automatically. *HMAC, Hash-based message authentication code. HMAC is a type of message authentication code, MAC, that uses a cryptographic hash function and a secret key to provide data integrity and authentication. It's used to verify that a message has not been tampered with and that it originated from a trusted source. In summary, hashing is a powerful tool with many applications in computer science and cryptography. Hash collisions are inevitable, but the likelihood of collisions depends on the size of the hash space and the strength of the hash function. MD5 is considered broken and should not be used for security-critical applications. SHA256 is still considered a strong hash function, but new and stronger hash functions, like SHA-3 and Blake3, are being developed. When hashing passwords, always use a salt and a KDF, bcrypt, scrypt, argon2. Understand the trade-offs between different hashing algorithms and choose the right one for your specific needs. This detailed guide should give you a solid understanding of hashing, hash collisions, and the differences between MD5 and SHA256. Remember to stay up to date with the latest security recommendations and best practices in cryptography. Cryptography is an evolving field.